Okay. Well, welcome to Physics 2820, Lecture 15. So today what I want to do is I want to build upon the knowledge of symbolic computing using SymPy that we went through on our previous lecture in Lecture 14. The idea here is to demonstrate how you can use symbolic computing to solve mechanics problems. And the way we're going to do that is by solving some problems that you would have seen in a previous mechanics course, like Physics 1050, and then solving more advanced or complicated versions of the same problem that you probably couldn't solve with the tools you got from first year calculus. But with the aid of SymPy, it makes them actually pretty doable, or at least tractable in some sort of way. Okay, so here we go. We're going to start by importing our standard libraries. And just to make it really clear whether or not I'm using a matplotlib function, a numpy function, or a SymPy function, I'm going to import SymPy with the short form of SP, so you know what the function is coming from SymPy. This last command is used to make sure that we're getting LaTeX-like displaying. Depending on what kind of software you're using, this may or may not be strictly necessary. But what this is saying is render the LaTeX as the output from SymPy using this JavaScript library called MathJax, which is basically LaTeX for the web. So we'll run that cell to get it going. And the first problem I want to study, and I've got about 10 of these in total to browse through, is a problem from kinematics. So you may remember that we covered these kind of problems when we were doing stuff in first year physics. We talked about two objects, one that's traveling at a constant speed and one that's traveling under constant acceleration. So you could have a scenario like a truck is waiting at a red light and there's a bicycle who's 10 meters behind the truck, and the light turns green. The bike is traveling at a constant velocity and the truck is accelerating. Because the bike is moving faster than the truck initially, when will the bike catch up to the truck? And then when does the truck overtake the bicycle? Because of course trucks go faster than bicycles. So here's how I would begin to solve that problem in a symbolic sort of way. Everything is from kinematics. And what we need to do when doing symbolic mathematics with SymPy is you need to teach SymPy all of the symbols you're going to be using. So for this particular problem, time is important. There's going to be some variable representing d for distance. We are given information about the velocity of the bicycle and the constant acceleration of the truck. So let's define 4 symbols. And so now we've taught SymPy that these are the symbols. We got to come up with some equations. So thinking about kinematics, we know that the position of the bicycle as a function of time is just the velocity of the bicycle times time. So what we're doing is we're defining an equation as follows. xb is equal to velocity times time. Now the truck starts off at a position of d meters ahead and then accelerates from rest with 1/2 acceleration times time squared. This is one of the known kinematic formulas for constant acceleration. So we can just sort of type that in all the way through. Now, if you want to look at a graph of this, you can't graph this and this directly without first substituting in particular values for VB, D, and AT. Now, some particular values are given to us in the question, 3, 20, and 3. So let's create a dictionary of parameters so we can substitute in these specific values for these general variables. If you read through the question, the distance d is in meters, the velocity of the bike is in kilometers per hour, and the acceleration is in meters per second squared. So let's convert those kilometers per hour into meters per second. There's no need to grab a calculator. You can let Python do the mathematics all the way through. If we take the position of the bicycle and substitute in all these parameters, we can plot it. If we take the position of the truck and substitute in all the parameters, we can plot it. And then look at a plot of the position of the bicycle as a function of time, that's the straight line, and a position of the truck as a function of time. The truck's accelerating, so eventually it overtakes the bicycle. The bicycle's moving at a constant velocity. So this is a position versus time kind of plot. Now you can look at the plot and you can sort of read off that these two lines are going to cross somewhere around 0.6 seconds and just past t equals 3 seconds. Those are the points at which the bicycle and the truck are in the same location at the same time. So to ask SymPy to solve this for us, let's solve the equation xt equals xb. That'll be the equation which we're going to solve. We've discussed it in Python or in SymPy. You can't write xt equals xb. That would be assignment. You can't use equal equal because that would be structural equality. You have to use this operator eq to define an equation. But what this means is the expression xt is equal to the expression xb. That's an equation. It's just basically taking these two things and setting them to be equal to each other. And then I'm solving it for all of the possible values of t which solve this system. So in SymPy, solve set gives me the complete set of all solutions that solve this equation. And the solution is, of course, just from the quadratic formula, VB divided by AT minus the square root of this, and VB plus the square root of this. If I want to turn those into something specific, I need to substitute in some parameters. And then, because of course this is mechanics and we want to pay attention to significant figures, let's print those numbers out to only 3 significant figures. And what you get is this first time is 0.656 seconds, and this second time is 3.05 seconds. So we solved the problem. And this is the kind of thing which you were able to do in Physics 1050. You're able to take these equations, write them down, stick in some numbers, apply the quadratic formula, and figure out these times. So SymPy can do this as well, but it takes the mental load of having to actually solve this algebra off from you and gives you a pretty nice plot all the way through. So that's a use of SymPy, but it doesn't give us anything that we couldn't have done before. Let's try a more advanced version of the problem where the bicycle is not traveling at a constant speed and the truck is not accelerating at a constant rate. So here's the scenario. Here's story number 2. Let's imagine that we have a truck which is sitting at a red light. There's a cyclist who is 3 meters behind the truck, and at the moment the light turns green, the truck starts to accelerate. Now the cyclist is trying to pedal very fast at a speed of 20 kilometers an hour, but the bicyclist has been riding for a while and is getting tired. So the velocity of the bicycle is actually going to start to slow down a little bit over time. Here's a formula for what the velocity of the bike is as a function of time. Let's suppose that it's equal to 4 times e to the t over 3 plus 2 meters per second. It's just an expression. It's a formula. It indicates the fact that the bicycle is slowing down with time. The truck is able to accelerate at the beginning quite quickly, but as it starts getting up to speed, the engine only has so much power, so its rate of acceleration is going to drop off with time. So its acceleration is not constant. And just for the sake of argument, let's suppose that the truck is accelerating with a rate of 2 minus t over 10, where t is given in seconds, and the overall thing has units of meters per second. How would we go about figuring out when the bicycle and the truck overtake each other? Well, to solve that more complicated problem, we would start this a similar way. We start by introducing any symbols we want. We might just introduce the symbol t and do everything with expressions. Let's define an expression for the velocity b. It's no longer a variable, it's a whole expression defined in terms of time. Again, notice that I'm using SymPy's version of the exponential function. It's a true exponential, not a numerical exponential. So there is the velocity of the bicycle as a function of time. And here is an expression for the acceleration of the truck as a function of time. First year kinematics formulas work for constant velocity or constant acceleration. We do not have any formulas in our back pocket that we covered in first year that tell us how to write down the position as a function of time if velocity and acceleration are not constants. What we can do, though, is we can know that the derivative position is the same as the velocity. So if you take this velocity that is this expression right here, and you integrate that with respect to time from 0 when it starts up to some later time t, that will be the same as the velocity. What we're saying here is position is the integral of velocity with respect to t from 0 to t. It might seem a little bit weird to have a t both as the dummy variable and the upper limit of integration, but this is fairly common. If you want, you could call this t star or t prime, and you're integrating from 0 up to t. The point is, this expression is the position of the bicycle, assuming that it starts at x equals 0 at time 0 at any point into the future. SymPy knows how to integrate. Likewise, if we want to figure out the position of a truck that's accelerating according to this formula as a function of time, we'd have to integrate twice. The integral velocity of an acceleration is a velocity, and the integral of a velocity is a position. So let's integrate the acceleration from t equals 0 up to t equals t. We're starting at an initial speed of 0, so there's no constant. To figure out the position of the truck, we're going to integrate this expression from 0 up to t, but we'll institute the fact that we know that at time equals 0, the truck is actually 3 meters in front of the starting line, in front of the bicycle. So we can come up with an expression. So the point is, this is the position of the bicycle, this is the position of the truck, and what I can do is, oh wait, I've got some lines of code that I was using for debugging. Just ignore those. Okay, we'll go with this. I can take these two expressions and plot them. And this is going to be the position of the truck. You see the truck here, it's accelerating. And then it actually starts to accelerate less slowly. And here's the bicycle, it's going at a constant speed, but it's slowing down. And so the question is, when do these two paths cross? When does this thing equal to this thing? For what value of time? Okay, let's do the same thing. Let's take those two expressions and solve for when they're going to be the same, and solve for t. Okay, and what we're getting here is a conditional set. Solve set is giving us all the solutions in the cleanest, most symbolic way it can do it. And what it's saying is, sure, the answer to this problem is t is any complex number which solves the problem. So the answer to the question is the answer to the question. It's not very useful, but that's the most compact way of writing down this as a symbolic expression. And the problem is, SymPy, nor us, can solve this transcendental equation. It doesn't have any simpler solutions. What SymPy can do, though, is take these equations and look for numerical solutions. So even though SymPy talks about symbolic mathematics, it can actually look for numerical solutions of symbolic equations. The only trick with nsolve, which is SymPy's numerical solver, is it can't solve all the solutions. It finds a solution near to some initial guess. So the way that it works is not sp.solveset, it's sp.nsolve. You give it the same equation, but then when you need to give it is an initial guess for the answer. So if I look at this graph, I see that somewhere near t equals 4, I could put t equals 3.7, but something in this region, there's going to be a crossing point. So I'm going to use an initial guess of t equals 4 and then evaluate that solution. And what SymPy is able to do is solve that transcendental equation and estimate it to 2 significant figures, or 3 significant figures, that the truck is going to overtake the bicycle at 3.72. If you wanted to figure out this point right here of when the bicycle first overtook the truck, what you need to do is give it an different initial guess time to be something much smaller, like a guess of 1, and what you would end up with is that time right there. And indeed, if you look at the graph, this point, yeah, I can believe that that's 0.59, and this point right here is 3.72. Okay, so you can see that we can use this combination of symbolic mathematics and numerical mathematics to solve something which on pen and paper would be quite challenging. Now, there's another approach. Rather than figuring out the velocity and the position with integrals, you could do what we've done for the rest of the course, which is to recognize that if you know what the position, the derivative of position as a function of time is, or you know what the second derivative of position as a function of time is, you can figure out the position as an ordinary differential equation. SymPy knows how to solve ordinary differential equations. So another way of setting up this problem would be to figure out what xb and xt are, the position of the bike and the truck, using ODEs. The way you would do that is you would say, okay, xb is a thing, but it's not just a number, it's a whole function. And so what I'm going to do when I'm dealing with ODEs, ordinary differential equations, is I'm going to tell SymPy that xb is a function, an undefined function, but a function. I set up an equation for the ordinary differential equation, and that equation is the velocity, which I already know, is equal to the derivative of that position. Differential equations need some initial conditions. Well, the bike at time equals 0 is equal to 0, so I can solve that system of equations, and I get that expression like we had before. For the position of the truck, the equation we want to solve is the acceleration is equal to the second derivative of the position. That's the equation of motion that defines what an acceleration is. Because this is a second order differential equation, I need two initial conditions: the truck position at time equals 0 and the truck's velocity at time equals 0. And I can solve that. Now, these two solutions are exactly the same as what we got back up here. No surprising, it's just a different way of approaching the same problem. If you want to go and plot this solution, you have to recognize that what it's giving you back as a solution is actually an equation. It's giving you back the equation xb of t equals this thing. When I go to plot this, I only want to plot the right-hand side of this equation. I only want to plot the right-hand side of this equation. So what I do is I say solution 1, right-hand side. Solution 2, right-hand side. And so if we run that code, we get the same pictures we got before. Okay, so this is just sort of setting up symbols, beginning to look at some integration, some kinematics problems. Let's go to another topic that we cover in first year mechanics: oscillators. Okay, so one of the things you could do is consider the following mechanical problem. Consider a block which is attached to a spring on a horizontally frictionless table. One of the things you know from experiments is that the more you pull a spring, the more it pulls back with a force that's linearly proportional to its distance away from its equilibrium. Mathematically, this is Hooke's law. The force is proportional to minus kx. Newton's second law says that the net force, minus kx, will always be equal to the mass times the acceleration. Since acceleration is equal to the second derivative of position, this leads to the following differential equation. So this kind of derivation is what we've done before in the course. F equals ma. I now have a differential equation just in terms of x, and I still need initial conditions, an initial position and an initial velocity. So this is using SymPy. This is just writing it out. This is sort of the derivation. SymPy can't help you with the physics. You still need to be able to do that. There is a solution to this problem that we quoted in Physics 1050. SymPy can help us recover that analytical solution. This is a differential equation. So because this is a differential equation, I want to start by defining this function x that I want to solve for, not just as any old symbol, but a symbol which is a function. The other variables that are involved in this problem, well, there's a time, so let's define that as a symbol. Let's define k and m as positive constants. And let's define initial position and initial velocity as two other symbols. So here's all the symbols we need to teach SymPy about. We write down this equation: the mass times the second derivative position, that's an acceleration, is equal to minus xt. That's the ODE as an equation. The initial conditions are x of 0 is equal to xi, and x prime of 0, that is the first derivative evaluated at 0, is equal to vi. If I take those two conditions and do a D-solve, differential solver, all the way through, what I'm going to get is the following expression. A good question was asked in the chat. Can you go over why you have positive equals true in the initial setup? The reason I have positive equals true is because SymPy does things that are mathematically correct. And I want to handle the situation because I sort of know that the answer has k's and m's that involve the square roots of k's and m's. I want it to do the simpler thing where the square root of m and the square root of k are allowed, right? The square root of m, if m is a negative number, those wouldn't be an option. And the square root of m or the square root of k, if they were equal to 0, that wouldn't be an option. So I'm telling it that mathematically, you have less you need to worry about. But you can always explore what happens if I didn't do that. Take a look what you get. If you don't restrict m and k to being positive real numbers, SymPy will give you back the general mathematical solution. So in general, if you let k and m be any number, that's the most general solution. And no, you might be okay with that. You might be okay with exponentials going back and forth. And what this means is if k and m, you actually get some imaginary numbers going on here. And if you're good with your complex analysis, this might be fine. But if I'm trying to get this written in a form with sines and cosines, forcing k over m to be positive turns these into an oscillatory solution. So that's why I put positive equals true. Okay. Now, when we typically look at this solution, this square root of k over m has popped up everywhere. We often write this with a special frequency called the natural frequency. The natural frequency is the square root of k divided by the square root of m all the way through. We can define this as omega naught is equal to the square root of k over the square root of m. We often write this equation down so that the k's and m's don't appear, but what does appear is this natural frequency. To get that into this equation, we could introduce omega 0 as a symbol. And what we'd like to do is a substitution. We'd like to say, okay, take this expression. Every time you see square root of k divided by square root of m, replace that with an omega 0. And that sort of works. It's not bad. It's taken this square root of k and this square root of m and indeed replace those two with an omega naught. It's taken this square root of k and this square root of m and replaced those. But this is a square root of m divided by square root of k. Well, you and I might be able to take a look at this and be like, no, that should just be 1 over omega naught. But SymPy isn't perfect. It sometimes needs a little bit of help. And these kind of substitutions, it's very odd to substitute an expression for a single variable. Typically what we do is we substitute a single variable for an expression. So instead, if you just take this and rewrite it and say the square root of k is equal to omega naught times the square root of m, same idea, then we can convert this expression into this expression. So now the k's and the m's disappear entirely. It doesn't really matter how you want to proceed, but these are things you can do within SymPy. Now, x of t is still just an undefined function. When we defined x of t way up here at the top, it was just some function. It was a function, but we didn't really know which function it was. If I look at the type of x, it is just a SymPy undefined function. If I want to take x and now have it equal to exactly this right-hand side, what I can do is take the right-hand side of that expression and actually bind it to a function and say t, or x, is a function that takes t and becomes the right-hand side. In the SymPy world, these are called lambda functions. Very similar to Python lambda functions, anonymous functions. It's a mapping that takes t and becomes the right-hand side. So let's call x equal to this thing. This is now the function. It's a rule or a mapping that takes t and maps it to this expression. Okay? It has now a different type. It's no longer an undefined function. It's now a lambda function. And the benefit of this is I can say x of t, and I get the expression. Or I could say x of 2, and everywhere there's a t, it gets filled in. So x of something is a function that I can use. Okay, now one of the things you might want to do with this is, if this is an oscillator, like simple harmonic motion, you should be able to show that the kinetic and the potential energy together are conserved. We know from first year physics that potential energy for the system is given by 1/2 kx squared, written in terms of that kinetic energy, of that natural frequency. That's 1/2 omega naught squared times m times x squared. And the kinetic energy is 1/2 m times v squared. Let's define two new expressions for potential energy and for kinetic energy. Potential energy is 1/2 omega naught squared times m times x, evaluated at t, times t squared. Now someone's going to ask me, why do I need to do rational 1, 2? SymPy understands rational numbers as being fractions. Python understands numerical things. If I was to say 1 divided by 2, in Python, that gets evaluated as 0.5. If I want to leave this truly as a rational number, the fraction of 1 divided by 2 as a rational number, a fraction, I can tell it explicitly, this is a perfect 1/2, an exact 1/2, not a approximate 1/2. That's why I've done SP rational 1, 2, any fraction, any numerator divided by the denominator. That's the potential energy. And likewise, 1/2 times m times the velocity squared, that is what k is. But notice what we've done here. I didn't type in v of t. I typed in the derivative of x with respect to t, because that's what a speed is, what a velocity is. It's the first derivative. SymPy has done the derivative for me. So now I have these two expressions. If I add these two things together, I'll get the total energy of the system. And one of the things we know about physics, or we'd like to show about first year physics, is the energy as the total mechanical energy of an isolated system should be constant. If I take that entire expression and I try and simplify it, I get a single value just in terms of its constants. And if you look at this, mass, natural frequency, initial velocity, initial position, those are all parameters, they're all constants. There's no variable time anywhere in here. Indeed, accelerate or position, energy is a constant in time. So this is the kind of thing we would have done, and we can play with these things. But what's nice about this is I don't have to actually do the derivative. It's keeping care of all of the initial conditions for me. It documents fairly well my thinking in the problem. First year physics is filled with inclined planes. My next 3 examples are all going to be on inclined planes. And in the beginning, you're going to recognize and be like, yeah, I know how to do that in first year physics. And by the end, I'm hoping you're going to go, I don't know how to do that yet, but we'll figure it out. Here's my problem. Imagine I've got a block sitting on an inclined plane. I know that the coefficient of static friction between the block and the wood that makes up the plane of the board that's inclined has a coefficient of static friction of 0.1. The free end is being lifted very, very slowly. At what angle will the block begin to draw down the board? Okay, so here's the setup here. Okay, so I'm going to just erase that screen for a little bit so we can draw this. What we've got for ourselves is we've got, oh, that's white. That's not useful. Orange. Nice Halloween color. Okay, so there we go. So there is a board, right? And what we have here is we have some angle, Okay, so this angle is theta. And the idea is we are very slowly lifting this board up. When the board is flat, this thing does not move. But we can look at the forces acting on this thing to figure out how it's going to behave. Well, there's always a force of gravity pointing down. There's going to be a normal force at right angles to it. And then the block wants to slide down this plane, but there's a restoring force due to friction. This is the static friction force which is keeping it from moving. As you continue to raise this board up higher and higher and higher, what will happen is the coefficient of friction, the normal force will decrease because the component of the normal force is set by the component of gravity perpendicular to the board. That means this frictional force will decrease, and the component going down the board of gravity will increase. There will be a point when this will no longer be in equilibrium, but the component of gravity pushing down the board will cause a net acceleration down the board, right? It doesn't happen at small angles because it'll be static, but as you lift it up, this is one of the ways you actually can go about figuring out what this coefficient of static friction is. It's a test. You put an inclined plane, you slowly raise up an inclined plane, you measure the angle at which this block begins to slide, that gives you the coefficient of static friction. Okay, so let's try and solve that problem, which hopefully you recognize from first year physics in a SimPy sort of way. We've got some variables: the mass of the block, gravity, a coefficient of static friction, and an angle. Just so we don't have any weirdness, let's make sure that all these numbers are nice, positive, real numbers, right? We don't want to have any negative gravities or imaginary masses or anything like that going on. The component of gravity acting along the board, that is this direction, right? So I'm just gonna come up with a little coordinate system here. If I'm imagining my coordinate system, if this direction right here, this is the R direction, okay? And this right here is R equals 0, sort of up along the thing. The component which is along the board that's gonna make this thing slide due to gravity, the radial component, is minus mg sine of theta. That's basically doing this triangle bit. If we consider the normal force, what we're dealing with here is the force that's of the gravity that's pointing down. This is the normal force due to gravity. Since the block is not rising or shrinking along this block, it's not raising off the board, the normal force, that is this green thing, has to be equal to minus the force of gravity pushing down. Okay? Notice how I'm really explaining where all these things come from in these notes. The coefficient of static friction is proportional to the normal force, but it acts in this direction. This guy right here, this is this static friction force. Right? That's what this represents down here. And what I want to know is the critical angle when this force and this force are exactly equal. That's the moment at which I increase the angle anymore, the block's going to start to slide. So what I want to solve for is the equation F radial plus F static, those two components, exactly equals 0. That's the critical angle for this problem. Okay, well, let's do that. Let's introduce those symbols, define these components, and solve this problem. Now, SimPy is a mathematical library. It's trying to solve this for all possible solutions. Nowhere in here have we restricted the angle to being between 0 and 90 degrees. And in fact, I'm not entirely sure that what this is supposed to represent. There's some exponential, there's some imaginary numbers going on here, and some arguments of mu over n and some logarithms. This could be the mathematical thing, but it sure looks very strange to me. I did some reading on this in SimPy, which is an open source package and still under development. It may have some issues solving trigonometric equations. Maybe it'll be fixed in a future version. There are other solvers bundled in. Before solve set was invented, and solve set is a function that tries to come up with all of the solutions, all of the possible mathematical solutions you can have from an equation. SymPy did have another function called solve that was a little more modest. Solve is a function that finds solutions. It's just not guaranteed to find all of them. If I use solve on that same equation, now I'll show you what you get so it's not too confusing here. You're going to get all of the solutions. And this is a little bit what we'd expect to see. For the problem of a raised inclined plane, the answer should be the arctan of something. Now, there is a list of solutions that solve is giving back to us. That's what the square brackets is. There is only one solution when you solve it. So what I'm doing is I'm taking out the first solution out of that list, and that's what SymPy is doing. Now, this might look a little bit different from the problem that you would expect to solve. If you were doing this with pen and paper, my guess is what you would end up with is an equation that looks like that. Specifically, there's a G, there's an mg here, and there's an mg here. This is the radial component of the friction. This is the radial component of the gravity. The m's and the g's cancel. And if you solve this, you figure out that mu is equal to the tangent of this critical angle, or the angle is equal to the arctangent of mu. This is the way we typically write it down. SymPy is giving us this answer. And I have to admit, that's not one that I carry around in my back pocket as a trigonometric identity, but I did sit down and work on it. If you use some tangent half angle formulas, you can prove that this is equal to that. It's just a different way of writing it down. And in SymPy's mind, it thinks this is simpler than that. It's not a human, it's a computer, and its algorithm came up with this as an expression. They are mathematically equivalent under a half angle formula translation. No matter, we'll proceed. This is the critical angle, and you could write it in either of these two ways. It does not matter. See your half angle formulas if you want to convert between the two. If I want to come up with a specific number, I have to evaluate this function for a given physical value of the coefficient of static friction. Well, in this problem, we're given the coefficient of static friction is 0.1. So let's evaluate this thing with mu equals to 0.1. This is the critical angle. Now, this is critical angle in radians. So if you want to write it down in terms of degrees to radians multiplied by 180 degrees per radian divided by pi, you get 5.71 degrees. So for this particular problem, with this low coefficient of friction, as soon as I raise the angle of the board to just under 6 degrees, my block is going to begin to slide. Okay, so all of this is a little bit of a refresher on the kinds of problems we did before. Okay, so the idea here is I've got a block. Let's draw my block. Okay, I'm raising up this angle. And what's happened is this thing has begun to slide. As this thing begins to slide, let's imagine that we have the additional complexity that now that it's begun to slide, we are still increasing that angle. Okay, you can imagine the experiment where it's hinged at the bottom here. We've been raising this thing up. At some point, it begins to slide, but now we continue to raise it up. You can imagine putting an inclined plane like a board or a block on it, raising it up. The block begins to slide, but you continue to make the inclined plane more and more steep with time. Let's figure out here how that problem is different. The difference in the first case is what we did is we very, very slowly raise this up. Now we're raising it up at a sort of constant rate. We're rotating this board at a constant angular frequency all the way through. So can you see how the problem's similar but a little more complicated? It's a moving angle. It's not static anymore. Okay. Same problem. You got a board, which is a mass, 1.5 kilograms. The block starts off at 30 centimeters away from the hinge. That is the point R equals 0 at the bottom of the block. Same coefficient of friction. But we're lifting it now not as at a very, very small rate, but at a steady rate. We're increasing the angle at a rate of 0.4 radians per second. So we're raising it up. What angle will the block begin to slide down now? It's not going to be the same as it was before. And the reason it's not the same as before is now you're in a rotating coordinate system. Do you remember learning about inertial and non-inertial reference frames? And all of the laws of mechanics work great in non-accelerating reference frames. With respect to the board, we're now in a rotating reference frame. As you take that board and rotate it up, you're spinning the entire system. A spinning system is non-inertial. There are forces that are apparent on the block because the system is rotating. If we're thinking about everything in terms of an inclined plane, and this is how we are defining the coordinate system along this line, if you are rotating this system, what you're doing is you're rotating this coordinate system. That means it's not inertial. If the whole system is rotating with an angular velocity of omega, then you're going to have to bring in some additional forces. Now, from the rest of the world, we would call these fictitious forces, centrifugal forces. In a non-rotating frame, we call this a centripetal force, but from the point of view of the reference frame that is rotating, it's a real force. From the point of view of R, this is a force that has to be included to account for the motion of the block. So if I've got a block in a rotating reference frame, there is going to be another force called the centrifugal force. Now, this centrifugal force has to do with a couple things. One is how far away the block is from its pivot, how massive it is, and how quickly it's rotating around. This is the centripetal acceleration of the system, which we know is mr omega squared. Okay? If you didn't want to put this in a rotating reference frame, you could also talk about the force static friction provides the centripetal acceleration required to keep the block moving in a constant circle, right? Because that's what's really happening is the block is now moving in this circle. So that's really what's going on. But I'm going to go into this rotating reference frame. Okay, in that rotating reference frame, here we go. Here are the parameters involved. We've got more going on here, but we're going to keep on extending. This problem involves mass and gravity and angles and mu's, but now also a variable of where the block is and how fast you're rotating the board. The components of force are very much the same. We have a radial force for gravity. We have this new centrifugal force, which is, from the point of view of the board, going to try and make the object slide up the board. We've got a normal force component of gravity. We've got a normal force of the board on the block, and we have a static friction force. In this rotating frame of reference, these three forces need to be in equilibrium for the block to stay on the path of tracing out a perfect circle. This can be a little bit weird, right? But what we're really saying is that is the balance of forces that if I had a block, it was right here, and I want to ensure that it's staying on this path of a circle, then I need to have the following forces in balance. The component of gravity, which is pushing down, the centrifugal force, which is sliding the thing away, and a force from keeping it sliding down. One is keeping it from sliding, and the other one is to keep it on this circle. All three of those things have to be in balance for it not to slide. There is an angle, though, at which the force of gravity will become too weak, for a static friction force will become too weak, and this will become too strong, and it will begin to slide. Okay, that's the mechanics to set that up, but let's see how SymPy can help us solve the problem. I need to solve the equation of when those three things are equal. Well, let's run it. We teach it all those equations and we solve. Okay, here we go. This is the set of equations we want to solve. And we'll try and figure out whether or not SymPy can solve this. Okay, it's a little more confusing, but not too bad. It's very similar to before. Gravity starts to actually take a role in this problem now. Gravity doesn't cancel out. One of these roots is physically meaningful, the one with a small positive angle. When it turns out it's this guy right here, when you work out the details, I'm going to give this a label of the critical angle. This is the physically meaningful solution. One's going to be a small angle, one's going to be a very, very large angle. We want the small angle solution. To figure out specific numbers for this, we submit some parameters. We know what G is, what R is, what omega is, and what mu is. So what I can do is I can take this expression and substitute it in. Okay. In the situation where you're not raising the board slowly, but you're raising it at a steady rate, the block is going to begin to slide at 5.99 degrees. So if you do this experiment and you don't raise the board very, very slowly, if it's very, very slowly, it would begin to slide at 5.71 degrees. If you did it very, very quickly, or at a steady rate, it would actually begin to slide a longer one. How would we be able to determine which of these solutions in the problem is physically meaningful? Oh, evaluate both of them. One's going to be the small angle, one's going to be a much bigger angle. Right, so this is a way of presenting the solution. We could do the whole thing here. Clearly, this is not the physical solution. This is just the other mathematical solution, right? I got an inclined plane. One solution is this angle. One solution is this angle, right? This is one solution. This is the other solution. So physically reasonable just means the one that's like that. You'd have to interpret your solutions just like you would solving any mechanical problem. You don't just look at this and say, oh, I know the answer. You look at the answer, you make a plot, you calculate it numerically, you figure out what to do, right? Just like you'd solve any problem in mechanics. So that's why I'm saying it's physically not realistic. Okay. Okay, are you good with the idea of a rotating board, a board which we're moving up? Let's keep on going. Let's work on the situation where the block is on a rotating board and now the block is sliding. Okay, so here's the scenario. We've got a board. Well, here's my board, okay? It is increasing in time. It is rotating around a pivot with a certain frequency. There is a box on here, and we are now past the critical angle where this begins to slide. So now there's going to be a velocity component down the ramp. However, the board is continuing to spin around. So at a later time, this thing has moved in this direction, right? So at a later time, the board is, well, that's terrible. The board is now here, and the block, right, has shifted down the board as it's rotated because it's sliding. You're now in a moving, rotating reference system. And this is something you'll cover in mechanics courses, this idea of centrifugal and centripetal, Coriolis forces and centrifugal forces. You do this in mechanics. I'm just showing you how you would tackle this problem numerically or symbolically. In a rotating reference frame where you have movement, not only is there a centrifugal force, but there's this other force called a Coriolis force. The Coriolis force is the cross product between the vector of the net force acting on, or the velocity in which this thing is going down the plane, and a vector which is along the axis of rotation. Now, I don't know if you remember how to do the right-hand rule, but you remember how if you get your hand, you put your finger in one direction, that's the velocity. You put your finger in another direction, that's the angle, that's the axis at which the angle is moving. And then the third direction is a force. The Coriolis force is in the same direction as the cross product of the velocity and the axis, which is parallel to the rotation vector. You will cover these non-inertial frames in a mechanics course if you have not already. Don't worry about it. Rotating reference frames will not be on some exam in this course. But given the equations, if they're given to you, you should be able to figure them out. The idea here is you're actually going to get a net force, which is at right angles to both of those things. So if you've got a force which is at right angles to this green vector and at right angles to something pointing out of the page, what we're talking about is a force which is into the board. That's the Coriolis force. And it occurs because you have a moving object in a non-inertial reference frame. Okay, how do we bring all this together? Well, I'll show you. Not only do we have a centrifugal force, but we also have a Coriolis force. And it's defined as the cross product between the velocity and the rate of rotation. And if you work out that cross product, see a course in mechanics, this is what you would get. What we have now is a moving block and a moving reference frame. We've got a number of functions. We've got all those same parameters and an initial position on the board, but now the position on the board is going to move with time. These are all constants. This R is the position as a function of time. So I'm going to define all these things and set up my equations. As before, we've got a radial component of gravity. It's going to slide down the board. That's the direction the force of gravity is going to point. We've got a centrifugal force that from the point of view of the board, it's going to slide up the board. In a rotating reference form, this is that feeling of you being pulled up the slope because it's spinning. There is a Coriolis force also in the problem. And what this does is going to press the object into the board. Because there is a board, there's a normal force due to gravity into the board as well. These two forces are pushing into the board. The board pushes out back on the block to keep it on the board. That's the normal force. Because it's not moving off the board, it's sliding along the board but not moving off it, these two forces together have to be equal to the normal force. Once you know the normal force, you can figure out the force of kinetic friction. Okay, and the point here is we have all these equations, but they're all being defined with something that by themselves you could make sense. So here is the net force. This is in the radial direction. This is the net force acting on an object. And of course, you know how to solve this kind of problem. And for the purposes of this course, this is where we would go. I would say some derivation. I would just start you here, right? One could do the derivation and come up with this. If I tell you that this is F net, what I need you to know is Newton's second law, which means you can set this thing up as an equation of motion. The net force, which depends upon some constants, which depends upon some things which are dependent upon time, and some other things which are dependent upon time. Because the angle is always changing, as well as the position along the board is changing. But that has to equal to mass times the acceleration. This angle, okay, is not a constant. It starts off at t equals 0 when the block begins to slide at a critical angle. So what I can do is I can take that critical angle we came up before, replace the symbol for r with a new symbol, r sub I, to make it very clear that this is the critical angle that it's going to start moving at, and then take this entire expression and replace the omega with a new equation, omega naught plus omega, not omega, theta naught plus omega times t. This is just the angle is increasing linearly with time with an angular velocity of omega. So let's do that replacement. Okay. This is where we are starting to really appreciate the power of a symbolic thing like SymPy. All the steps are not too bad, but we've got this expression, which is looking a little bit wary. We've got some arctans and some sines, some square roots and symbols. Even just copying this out on a paper would be a bit hard. The important bit is you've got some forces. Okay, that's a gravity force. This guy right here, I'll do this. We've got a gravity force. We've got a centrifugal force. And this guy right here is your friction force. You see there's a mu right there? This is your kinetic friction force. This is slowing it down as it slides down the block. Okay, let's see if SymPy can solve this thing for us. So I'm going to set up an equation. I'm going to take this F net. I'm going to have it equal to mass times acceleration. Second derivative position is acceleration. I'm going to substitute in some initial conditions. It starts at time equals 0 at initial position Ri, and the first derivative of Ri is 0. It starts at rest. Now this is SymPy doing some work for us. Now usually, when you get this black thing to go black and the answer doesn't come out right away, you might think, is it crashing? Is it broken? Nope. In this case, it's just doing some work. So there's the solution. Because doesn't everybody know that R of t is equal to this mess? And I don't know about you, but I would never want to go from this equation to this thing and even hope to get the details all right. We've got exponentials and square roots and arctans and t's. This is amazing that this is doing. Yikes, this is a scary formula. To make it tractable, let's take all the constants, the g's, the mu's, the omegas, the initial positions, and substitute those in. How do we do that? Well, let's create a dictionary. It's going to say, for every one of these g's, we're going to substitute it in. Omega is equal to this, mu is equal to that, Ri is equal to that. Take this entire solution and substitute those in. A little bit better. And would you believe that with those coefficients, the position is given by an exponential plus a sine plus a cosine, and then another exponential. Way better to visualize this as a plot. So if I just plot the right-hand side of this guy, here is the function for position as a function of time all the way through. So what you see is, as it is sliding down the inclined plane, it will hit the inclined plane, or it'll hit the bottom at a time of 0.77. So if you were to physically do this experiment of having an inclined plane, right, and you were to rotate that inclined plane at a constant velocity of omega, and you were to have a block which would not initially be moving, but then starts to move when it hit a critical angle, and you measured how many seconds it would take to go from here all the way down to here, and you measured that time, we have just now figured out that's the answer. I think that's pretty awesome to be able to do that kind of thing. You still need to do the physics. You still need to set up the equations. But what SymPy is doing for you is helping you with all of the mathematics. As long as you got the physics right, SymPy is helping you do the mathematics, so you're not making a mistake anywhere. So you can see what happens is the position starts to actually move very slowly. But of course, as you increase the slope, it starts to fall straight down and fall quicker and quicker. Cool. At least I think it's cool because I like physics. Okay, let's move away from inclined planes and just do a couple of other problems. First of all, momentum. These aren't hard problems. These are exactly what we would have seen in first year physics. But you remember doing collisions? Collisions are the idea of two objects hit each other, and we want to conserve conserve momentum and conserve energy. So imagine I've got two carts on a track. I know the masses of each, and they bounce off each other. Conservation of energy is that equation. Conservation of momentum is that equation. So to solve this or put this into SymPy, I need to define a number of variables, the masses, the velocities, all the way through. Again, I'm using an equation because I can't say equals equals in Python. This is a statement of the conservation of momentum. In a collision problem, you've also got the conservation of energy. Here is a statement of the conservation of energy. I can solve this pair of equations using SPSolve. This is how to indicate a pair of equations and give me back and solve these two pairs of equations for these two variables. There's lots of things here. You're telling Solve which variables you want to solve for. Well, in a collision, I know the initial velocity. I want to figure out the final velocities. So if I solve that, I get the following solution. Now, it's giving me two mathematical solutions. The first mathematical solution is when the final velocity is the same as the initial velocity. This is the situation where the two carts start off on, and they're never going to impact. This is just the situation that you've got an inclined plane and you've got two carts which are sitting on that inclined, or not inclined plane, on this plane. There's one cart. We're going to call that cart 1, and we're going to call that cart 2. This first solution is the situation where these guys just start going in opposite directions. Well, if they start by going in opposite directions, their final velocity is going to be their initial velocity. They never interact. This solution is the one where they hit each other, where they trade momentum. So we're going to pick this second solution. You have to interpret the two solutions. So let's do that. Let's grab that second solution. Okay, put in some parameters, grab that second solution, and take a look at what these things are. And here we go. If you collide two cars, they're going to bounce with minus 1.1, and the final velocity of the second car will be 0.41. This formula is something that you could derive with pen and paper, but it gets a little nasty. So the arguments for SP are always left-hand side and right-hand side? Yes, exactly. Whenever you deal with an equation, it's just left-hand side, right-hand side. You also could just say this minus this by itself, because equations with no right-hand side are assumed to be equal to 0. Okay, so that's just equations, and you might recognize a little bit of these things going, okay, yeah, I can see how you could come up with this with pen and paper. Let's do something a little bit fancier. Let's not model just the collision between two things, or the before and after state. Let's model the actual details of the collision, as in what happens to these two carts as they are colliding. Okay. Suppose these two carts are equipped with some magnets. And so because they're equipped with a magnet, there's going to feel a repulsive force as the two carts get close together. In the sense that if the cart is here and the cart is here, let's attach a little magnet here and a magnet here and orient them in such a way that we basically get north on this side, south on this side, south on this side. When these two carts start to get close together, they're going to feel a repulsive force. You could build this with a spring as well, but this is a way of conserving momentum and having these two carts interact with each other. Basically, they're going to bounce together. Now, before and after the collision, the interaction between two objects, momentum and energy still need to be conserved. That all stays the same. So I can do that. But now what I want to do is solve not just for the position, for the velocities after the collision, but the positions through the collision. I'm going to figure out where these two objects are. It's basically all about forces. The force of cart 1 on cart 2 depends upon the repulsive force between the two of them. We're given in the question that the cart feels a repulsive force equal to 0.1 divided by the distance between them squared, or to the power of 4. So this force is minus 1 divided by the difference between those two positions to the power of 4. That's the net force acting on cart 1. The equation of motion for cart 1 is mass times acceleration equals the net force. The parameters for cart number 1 is it starts with a given mass, an initial position, and an initial velocity. Do the same thing for cart 2. Because of Newton's third law, the force of cart 2 on cart 1 is the same as cart 1 on cart 2 with a minus sign. So, but we figure out that force, come up with an equation of motion, and know some parameters. If I solve this system of equations, basically trying to solve this system and this system together, SymPy is going to say not implemented. It basically says, you got me, I don't know how to solve that. To be honest, I don't know how to solve that system of equation either. It's nonlinear. It may not have an analytical solution, or at least one I don't know. But we can use these systems to come up with a numerical solution. One of the things we talked about in numerical solutions is there's a lot of solvers out there. Not only can we write solvers like Runge-Kutta order 4 or Richardson-Taylor or Euler-Richardson, you can actually use prepackaged solvers. So if I take these equations that I've derived, these guys right here, I can actually stick those in to a function like ODE_int to have it integrate these solutions. We talked about this a few lectures ago, that a generalized way of writing a solver is write a program that just takes the right-hand side of this system of equations. Remember that when we're solving ODEs, what we're doing is we're solving the system of equations. The derivative of the first thing with respect to t is equal to its velocity. The derivative of the velocity is equal to the net force on 1. The derivative of the position of the second thing is equal to its velocity, and the net force acting on this guy is equal to the net force right here. That's a system of 4 equations and 4 unknowns. Differential. These are all the right-hand side of this system. This is what a solver needs to know. So using this built-in solver into SciPy, you're basically just passing in the right-hand side and declaring x1, v1, x2, and v2 as the state of the system. Point being, you can use numerical tools when you can't come up with an analytical tool. And what you can see here is this solution shows you as a function of time what the position of these two things are. So what's going on here is one thing is moving towards the left, one's moving towards the right. They collide. They don't actually need to touch for a collision, and then they move on. If I take those two things and look at not only their positions, but their velocities, it makes it a lot more clear. They're basically bouncing off each other, and this is what's going on during the collision. There's an exchange of velocity as the two join together and move with the velocity of the center of mass, and then they exchange again. So what we're doing is we're modeling what's happening in the interaction. The final velocity of each things, well, that's exactly the same as what we had before, minus 1.1 and 0.4. The error is very, very small. Okay, just looking at the time, I'm just going to very quickly point out that I could do these collisions in 2D. But I think I'm going to skip that problem for today, but go ahead and take a look at it. It's the same idea. We're just doing a collision now in 2 dimensions all the way through. Oh, that's 8. I only have 9 problems. Good. I want to get to this last one. Isn't 10? It's only 9. I want to get this last one before we're done. Here's a neat little physical problem. Here's the scenario. Imagine I've got a platform, a table, and on that platform, there is some rope, okay? The rope is coiled up here, and someone goes and leaves a little bit of the rope hanging off the side, okay? How much rope is being left off the side? Well, initially, there's only a little bit of that rope, and that amount is 10 centimeters. Now, if this rope isn't very heavy, there will be a force of gravity pulling down on that rope. How much gravity? Well, it's going to depend upon the mass contained in here, and it will start to accelerate. But as it falls down, what will happen is the rope will have to start to get a bit longer, right? We can draw in a thicker rope. All right, we're going to start to get a little bit longer. Now the force of gravity acting on this thing, there's more mass for it to fall. But there's also more mass for it to accelerate. This is a problem that requires a more complex version of Newton's second law. We actually did talk about this in first year physics. We just don't tend to solve very many problems with it because it's sort of hard. Newton's second law in its full form says the change in the momentum of a system is equal to the net force. Not F equals ma, not force is equal to the second mass times the second derivative of acceleration, but the true form of Newton's second law is the net force is equal to the change in momentum, the derivative of the mass times the velocity. Mass times velocity could both depend upon time. So this is a scenario where we've got something that's falling that's increasing in mass in time. The little bit of rope that begins to fall, but a while later, as the rope is moving, the whole thing has velocity. This is important to understand. It has velocity. It has acceleration due to the acceleration due to gravity, but the mass of it is increasing as the rope uncoils and you get more mass that has to be accelerated. Newton's second law says the rate of change of momentum is equal to the net force. By the product rule, mass times acceleration squared plus the derivative of mass times velocity squared is how you would write out Newton's second law. Okay, let me show you how we would solve this problem with SymPy. Define some functions and some parameters. We've actually got 3 variables now, mass, position, and v. I could define what my Newton's second law is. There's my momentum, and set up an equation. This is the equation according to Newton's law. We have to be a little bit clear about how we've set up this problem. If I set this problem up so I've got a table, and I define this total length to be the variable h, and I set up a coordinate system, okay, like that. This is the y coordinate system, okay. Y is equal to 0 is at the bottom. It starts here. This is the position of the whole thing. I need to figure out how long the rope is. The rope is going to be h minus y. That's just what I've done right here. To figure out the mass of the rope, I'm substituting in its density times how long the rope is that's been draped over the side. Okay. When it does this substitution, it hasn't actually done the derivative yet. You can force the derivative to be done by asking SymPy to take that equation and actually evaluate things. The way it's done in SymPy is you say, do it. What this will do is take that equation and actually evaluate this derivative right here all the way through. R times h minus y of t. Well, r and h are constants. R is the density of the rope. H is the height of the table. The derivative of h of y right here would be dt dy, or dy dt. So you end up the square of the derivative. So we can simplify those things for you. Now, I can solve this problem analytically. I can solve for this, or I can try to. I can try and solve for this problem all the way through. And we get another not implemented error, which means SymPy doesn't know how to solve this thing symbolically. But it can be used to help us solve it symbolically if we use what we've derived to figure out what this equation would be in terms of y's and v's. That is, we take this equation. Okay, so there is the full equation of motion. And rather than dealing with the second derivative of y, replace that second derivative with y with the first derivative of v, and replace these derivatives of y with v, do a substitution, I can come up with a single equation that has y's and t's in them. And then I can use SymPy to solve this equation for the velocity. This is an equation for the velocity as a function of time. Specifically, the derivative of y as a function of time. What we're really doing here is we're able to define what the rate of change of one of the two variables in the problem is, position or the velocity. The details of how to do this, we can take this equation, we could do lambda phis we talked about before, which is a way of taking this expression and turning it into a Python-like function, something that would take these variables and spit things out. This function, what this is, can be evaluated at any position and any velocity, and it will tell us what the velocity or the rate of change of the velocity will be at any point. I'm feeling rushed. To go back through these things, what we're doing is we're using SymPy to come up with a system of equations to let us solve for this problem. We've thought about what the variables involved are, position and velocity of the rope. We know that the rate of change of the position is equal to velocity. And what we've derived is the rate of change of velocity is equal to this expression up here. Once we've done that derivation, what we can do is then use a numerical solver where we put in v as one of our state variables and y is one of our state variables, where explicitly the right-hand side of that system of equations is given by this expression. Pushing that all through a generic solver, we can solve it numerically. And here's the punchline where I want to end. This blue line is the position of the rope, the end of the rope, as it goes to on the bottom. And what it's really is showing is as you've got a rope that's hanging over a side, and there's a coil of rope right here, as this is moving down, it's going to fall. But if you compare that to the speed at which a single particle were to fall, that's free fall. The orange line is what a single ball dropped from a height of just under 4 meters would be. The blue line is what a rope that's being uncoiled would fall at. And it falls slower because it's having to accelerate the entire rope and its mass is increasing. Anyways, different things to play with. So all of this is supposed to be just a little bit of examples of ways of manipulating symbolic expressions as we derive our equations of motion so that eventually we can do things numerically. There's a lot of content here, and you might go, what am I supposed to do with this? At the end of the day, what we're going to do in this course is we're going to let SymPy help us with some derivatives and set up some equations of motion so that we can continue to solve them numerically. It's working with those numerical solvers is what we're going to deal with. We'll come back to SymPy when we need to derive what the net force is between many objects in a system, specifically when we talk about the three-body problem in celestial mechanics and the n-body problem in molecular dynamics, which is what we're going to end the course in. I'll come up with a couple assignment questions on this. You get the sense of it. But a lot of this is just be aware that these tools exist, and they can be useful, especially when the algebra and the calculus start to get very gnarly when working on mechanical problems. Okay, so that concludes this lecture on symbolic Python and doing that kind of stuff. We're going to dive into a lab. My experience from the lab on Tuesday is everybody was done in about an hour. Kyle, were there any issues with the lab? No, he's shaking his head. It was all pretty good. Again, I'll be around if someone wants to hit me up on the chat to talk about things, but most likely Kyle's got it all in control. We'll see you on Zoom on Tuesday for a more numerical lab and application. I'm going to talk to you about seismology, another geophysics application on Tuesday. And then the Thursday, I'll have us all gather together in the classroom again. Okay, thanks very much.